Welcome to ECE 220, Electric Circuits at the University of Arizona. You are listening to Hal Tharp, and I will be your instructor this semester. In this short video, and really the initial video, I want to provide a course overview. Typically we'll have more than one goal in a video, but in this particular video I really just want to set the stage, try to give you a big picture view of what we will be learning and working through in ECE 220. The context is really in terms of the curriculum here at the University of Arizona. ECE 175 is our computer programming class in C, and that provides this foundational material for our computer engineering subjects. Likewise, ECE 220, Electric Circuits, provides foundational material for the electrical engineering material. And in particular, we are using a textbook by Nielsen and Rydell, and in this class, ECE 220, we will be covering the first 9 chapters in that textbook. Now, what kind of material is associated with electrical engineering material? One diagram which really illustrates one of these sub-disciplines within electrical and computer engineering is this communications system that shows all of these interrelated and interconnected systems. You have underwater cable, you have telephone poles, you have cell towers, all of these, you have your cell phone. I don't know if anybody still has a landline, but you could have a landline. All of these systems involve circuits, which is the material that we will be covering in this class. A communications class here would be ECE 340A, and in fact that class is sort of 2 classes beyond ECE 220. The class that follows ECE 220 is in fact ECE 320A, and that covers the last few chapters, chapters 10 through 19, however many chapters are in the book. But in that class, it picks up with where this class leaves off, which is in power systems. And you can also see some power systems in a technical elective class, which is 414A, dealing with solar and solar energy, solar collection, etc. Power systems is one sub-discipline within electrical engineering. Communications is another. Computer systems, obviously you have to have both 175 and 220 to feel comfortable with going forward in computer systems. The computer architecture class 369A depends on these two in addition to the digital logic class 274A. Controls is another sub-area within electrical engineering. In fact, controls you could find in many of the different engineering disciplines: mechanical engineering, chemical engineering, systems and industrial engineering. A lot of those disciplines have a controls class, and in fact those controls classes a lot of times take on the character of the discipline that they are housed within. For example, mechanical engineering might emphasize mechanical systems. Electrical engineering, we might emphasize some electrical systems, but in fact we deal with mechanical systems, electromechanical systems, etc. We've already talked on power systems, but power systems takes off from where this class leaves. We will get as far as sinusoidal steady state. What is coming out of the wall in your home, that's some sinusoidal waveform. How do we analyze that relative to power? That's 320A. How do we analyze it in sinusoidal steady state? That's what we want to get to in this particular class at the end of this class. Signal processing. How do you manipulate signals to allow you to basically exchange information effectively or convey information? Signal processing could involve audio signals, it could involve images, etc. Electronics, how do you build the next neat device that involves transistors, diodes, etc. We will deal with some diodes in our labs in ECE 220. ECE 220 is a big class. It has lecture components and lab components, and it also deals with your homework assignments from the textbook chapters 1 through 9. The other subdiscipline within electrical engineering that I will mention is embedded systems, Internet of Things. You could think of that Internet of Things really does connect hardware with software. Embedded systems does the same thing with, now you maybe are programming smart devices, but those smart devices usually are interacting with other things, a lot of times humans, but sometimes inanimate objects. You now have these embedded systems that consist of hardware, brains, or intelligence. You want to know, how do you make that interface work, and that usually involves knowledge of electric circuits. All of these systems, please don't think that, oh, I'm just going to go into power and that's all I will ever see. Usually these areas, and even the general engineering disciplines, mechanical, chemical, systems, they all have to work together. They interact. There's no difference in the subdisciplines within electrical and computer engineering. So all of these electrical systems are interacting, and so you can't just say, oh, I'm just going to do electronics. You probably need to be able to interface and interact with other people, other subdisciplines within electrical and computer engineering, and also in other areas of engineering. One way, in just like one device, that you could see this explosion of interaction is in your vehicle. Here it's loaded with sensors, and how do you allow those sensors to measure or sense different properties or characteristics of the environment? And how do you get that information into a form that you want to have it in so that you can manipulate it and work with it? For example, now we have maybe adaptive cruise control. Maybe we have collision avoidance. Maybe we'll have automated highways, or maybe we already do. That might be sort of this control subdiscipline, but if we have radar involved with this distance measuring between vehicles for the adaptive cruise control, then we need to understand some electromagnetics, some radio frequency information. Likewise with security systems, lane departure, navigation and trip. Now we're maybe communicating with GPS, climate control, communication. All of these are subdisciplines that have to be able to work well together, that are interacting together, and you need to have as a foundation to be able to communicate and work with people in those areas is a foundation of electric circuits. Here's just another graphic that tries to pinpoint the sensors that are distributed everywhere in your vehicle. Can I illustrate interactive systems anymore? Did anyone get on a plane recently? Maybe not so much now, but when we are dealing with air, planes, and transportation, there's a lot of interacting systems. There's primary controls, secondary controls. How do you get this plane off the ground? How do you manipulate? Maybe you're doing it with wire. Maybe it's not mechanical linkages anymore with that the pilot has to manipulate. How do you get those signals to the right location in the plane and performing the actual commands that you want them to perform so that you have effective and accurate control of any given situation? That brings us now to electric circuits, ECE 220. Again, I said this is chapters 1 through 9 of the textbook, and in the first 4 chapters we will be dealing with circuits that are looking like this particular schematic, where on the left we have some voltage source. Let's say that's capital V sub S, and these squiggly lines, maybe they should be drawn a little bit better. Those are now modeling resistors, and those might actually be some other heater, for example, that we're modeling as a resistor. There's now voltage drops across each of those resistors, and this resistor may not be the same in value as R sub 2. Let's say that we have 3 unique resistors. The voltage source, V sub S, is in this particular diagram, and in these early chapters will simply be a constant source, and that is illustrated by these straight lines, and the long lines sort of are showing this cell type characteristic. But here in the first few chapters, our source will be constant, or DC, direct current. And if that's the case, then we might be interested to know what happens when we apply a constant voltage to this circuit. Let's say that our supply voltage, that's supposed to be a horizontal line, is given by V sub S. Now we might be interested in, okay, what's V sub 2 look like? Does it look like this? Does it look like this? No, in fact, with a pure resistive network or circuit, it's going to be a constant waveform itself, and it will be somehow dividing the voltage, the source voltage V sub S, and we'll learn all of these techniques. We will find or develop analysis tools that will allow us now to determine, okay, what's the current going through that resistor, and if I know that current, then I can use Ohm's law to find that voltage V sub 2, and it will be a fraction of this supply voltage V sub S. We want to now be able to analyze such circuits that are interconnected resistors and constant voltage sources. We then move into chapter 5, which allows us to introduce another circuit diagram, this triangle, that now has plus and minus labels associated with it, or the plus, the non-inverting input terminal, the minus, the inverting input terminal. What's typically not necessarily shown is this operational amplifier or maybe you've heard of op amp, is supplied, and now maybe I'll get this wrong, but let's say this is V plus and this is V minus, meaning I'm not sure how we will show this in the schematic in the labs, but you have to now supply these operational amplifiers with power from external sources. And the reason I say I might get it wrong, maybe somebody will label that V plus and this V minus, but in some way you have to now energize this operational amplifier. This again is chapter 5 material, and this, why do we need that? Well, now this is doing or performing what the description of the device actually says, operations. It now allows us to operate on signals, and in particular we will learn the relationship between the output voltage and the input voltage, and in this particular interconnected circuit, that's now simply a ratio of those two externally connected resistors around that operational amplifier. It's going into the inverting terminal, and that actually produces this inverter or this minus sign in addition to the gains R2 or the resistor values, which are now in a ratio of R sub 2 over R sub 1. So in fact, this operational amplifier allows us to scale these signals V sub in versus V sub out. And how we scale them, we might scale them down, we may scale them up. In the previous chapters with just purely resistive circuits, we were able to scale them down, but now maybe with this operational amplifier, if we choose R sub 2 and R sub 1 appropriately, now maybe we can scale it up in magnitude. Obviously it's going to have a negated value from the input voltage. That's a result of this inversion or negative sign in front of this operation of scaling the signal. We can now scale up or down, and we can combine, add, and subtract different input signals to allow us to manipulate waveforms. We could also introduce a sinusoidal input, Vn, and if it is connected the way the previous circuit was, it has this inversion. So now negating or inverting that input Vn, you see that the output is an inverted copy of the input, and if it's scaling up, the amplitude of that dashed or output voltage is larger than the input voltage shown in blue. Now obviously we can't get something for nothing, and that's why these externally applied supplies that energize this op-amp allow us to scale things up relative to an input voltage. That's chapter 5. And those, so far, we've simply just used resistors. We will then introduce a couple of new devices, inductors and capacitors. Here I'm showing a capacitor that's just two plates in this schematic. This is now material that we will learn from chapters 6 and 7. This schematic is interconnected in a way that illustrates a low-pass filter or implements a low-pass filter. These inductors and capacitors are energy storage elements. They now allow us to store energy and give it back, store and give it back. And now you can see that my input voltage source is not just flat lines. Maybe I want to put in a sinusoid. Maybe I want to put in constant values. What now happens when we energize this circuit with some voltage Vn? What does Vout look like? Suppose again, just to be consistent, we apply a constant input and we turn it on at time 0. That's what this is indicating. Here is now, let's say this starting time, time t equals 0. What happens to Vout? Well, now because this capacitor is an energy storage element, it doesn't instantaneously achieve its final value. In fact, it needs some time to charge up. And so now the output voltage might have this shape, this exponential shape, which is now, people will just say, oh, it has an RC characteristic. That's what they're meaning with respect to this behavior. You now have this charging up effect, and now we have to move beyond just algebra and algebraic equations when we have energy storage elements. This is why you need the differential equations. Now we have differential integral equations, and we need to understand how to solve those so that we can then obtain these output waveforms for given input waveforms. We will then step it up a little bit and say, okay, let's combine not only just a capacitor, but let's throw an inductor in there. This is now moving to the next chapter. And if you remember, we said we're going to have 9 chapters. We're almost getting close to the end. Now we have an inductor and a capacitor. They're both energy storage. We may have energy storage in the magnetic field of the inductor. Maybe we have energy storage in the electric field of the capacitor. They're throwing this energy back and forth. We apply an input Vn. Suppose that we, again, to be consistent, have some constant input into the system. What happens at V out? Well, now it doesn't have this RC charging look. It could, depending on the values of L and C. Now maybe it has some oscillatory behavior. This is now our output voltage on that capacitor. And what the output voltage looks like is going to obviously depend on the specific or particular values of R, L, and C. It may, depending on R, L, and C, it may have that first order type RC behavior. Generically, if we have an underdamped system, that means that we are going to have this oscillatory behavior. Then that's going to depend on how R, L, and C are valued relative to each other. That's chapter 8, and that again will depend on your knowledge of differential equations. We finally get into chapter 9, which allows us to interconnect, use all of the analysis tools that we've been using up until this point, but now we have to do that using our understanding of differential equations. Now we have second order differential equations, third order differential equations. How do we analyze these? Well, we will look at this now. If it's a third order, fourth order system, we are going to now restrict our input sources to being sinusoids. So that now, and we will in fact, let's say this is, and that should have been drawn a little bit better. Let's say that it's the same positive as it is negative. We will now assume this is in sinusoidal steady state, which means that this sinusoidal input voltage, Vn, has been in existence for a long time until we've reached a steady state. If that's the case, now what happens to Vn? Well, Vn isn't necessarily aligned with the peaks and the troughs of this input voltage. Now maybe it is delayed, and its amplitude may be less, it may be bigger. Generically it will be less, but we now can see that we have a delayed output voltage, and we will then have to figure out how do we analyze this. I said, oh, let's do differential equations. Now we have 10th order circuits or 10 energy storage devices. Oh, well, what we will learn is we can actually still do the algebra or convert this analysis into algebra by using complex numbers. So if we now understand how to convert sinusoids into complex phasor descriptions. We will then convert these inductors and capacitors into complex impedances, which are generalizations of resistors. Those impedances now are dependent on frequency. That now is what produces this non-alignment. The peaks aren't lined up, the valleys aren't lined up between the input and the output. This now has some delay associated with it, or phase shift. We'll learn how to communicate between delay and phase shift, etc. But how do we do that? Now we are going to need to perform this using algebra. That's why we want to start learning complex numbers, so that all of our strategies that we've learned up until this point, we can now generalize and use them the way that we were doing with resistors. It's now we have generalized resistors, which are impedances associated with inductors and capacitors. Using complex analysis, we will be able to do that for the sinusoidal steady state condition. I should just note that hopefully you will feel like this foundational material has a lot of different applications. I may fail to remind you of that, but at the beginning of this, remember, I showed you a car, I showed you an airplane, any, let's say, system. Many of the systems that you interact have some kind of circuit associated with them. Just think about those as you're walking through or working through this material. In terms of the textbook, for applications, again, look at chapter 1, but every chapter usually has what's called a practical perspective. Maybe it initiates or motivates the material in that particular chapter, and you may have to work through that material and then at the end read up at the end of the chapter, oh, now that we've learned what we needed to learn in this chapter, how is that applied in a real world setting? Just keep in mind that this material does have applications. If I fail to remind you of that, go back and look at the book and say, how is this even applied? What's the use of this? Go back and look at the practical perspectives, chapter 1, and even now you have access to a lot of information on the internet. You could now start investigating what are the practical applications of electric circuits. Hopefully that now motivates you to attack this material and learn it so that we're all successful at the end of the class.